Hello. As an IB Diploma Mathematics teacher at Melba Copland Secondary School in Australia, I was interested in something that would challenge and inspire students in mathematics, as well as encourage the IB student learner profile and adequately prepare them for a future of rapid change. This inspiration led to a question. As mathematics teachers, how do we prepare students to deal with a world of rapid change? I've been inspired by a number of educational philosophers. Dr. Farah Panwani, in his IB position paper, has advanced the idea of the cultivation of imagination, contending it's a prerequisite for empathy and ultimately international mindedness. As an IB examiner as well, I also adopted the IB internal assessment marking rubric because it's really good for encouraging creativity. In addition to another educational philosopher, Charles Fidel, also has inspired me. He advocates the development of students of what he calls the 4 C's of creativity, critical thinking, communication and collaboration as a means for dealing with the world of rapid change. Also Mike Lambert, who promotes the use of technology, allowing students to learn how to learn. Consequently, I'm particularly interested in the cultivation of imagination through technologies including digital media. Linking all these, I presented this as an assignment for my Year 11 Specialist Maths class. The idea was to encourage creativity using digital media in an open-ended investigation. The assessment involved an open-ended group investigation which was to be presented as a video to the class. The students could choose an application from the topics they'd just studied, that was trigonometry and polynomials. The students worked in groups of 3 and they had to submit an 8-page review of the mathematics involved in the application to provide maths rigour. They also had to do a validation test and ultimately the opportunity for creativity, the video they had to present to the class. I will now present the video, voted best by the class, to allow you to determine whether my goal of encouraging creativity through open-ended investigations in mathematics using digital media was a success. Thank you for your time.
Hello, my name is Jeremy, and I'm here to talk to you about the small angle approximation. The small angle approximation uses the basic trigonometric functions and approximates them. These approximated functions become more accurate as the angle approaches 0. This can be used in many areas, such as mechanics, electromagnetics, optics, and cartography. It is also used in astronomy and is still widely used throughout today. The idea behind it is that as the angle approaches 0 radians, the opposite approaches a value of 0. Therefore, as the angle approaches 0 radians, we can say that the hypotenuse approximately equals the adjacent. Therefore, sine theta approximately equals tan theta, which approximately equals theta. In astronomy, the small angle approximation can be used to calculate the diameter of planets or distance between 2 objects. The closer the angle is to 0 degrees, the more accurate the approximation becomes. It works in astronomy due to the fact that most of the angles that are used there are incredibly small. By understanding geometry and the nature of circles, it is possible to determine the distance to an object or the physical diameter of objects in space. In astronomy, the sizes of celestial bodies are commonly measured by their angular diameter relative to Earth, as opposed to their absolute size. Angular diameter is the angle that an eye, or camera, needs to rotate in order to look from one side of a circle to the other side. Stellar parallax is another way that the small angle approximation is used to calculate the distance of stars. Parallax is the observed change in the position of an object, which is the result of a change in the position of the observer. A good analogy is walking down a path with trees on one side and mountains in the background behind them. As you walk down the path, the trees would appear to be moving past at the speed you're walking, whereas the mountains would appear to be moving at a much slower rate, even though in reality they are both moving at exactly the same rate. Specifically in the case of astronomy, it refers to the apparent change in position of a nearby star as seen from Earth. The parallax of an object, in this case most commonly a star or planet, can be used to approximate its distance from Earth. From the surface of the Earth, parallax angles of less than 0.01 are difficult to measure because of the effect created by our atmosphere. This limits our telescopes based on Earth to measuring stars only about 100 parsecs away. Orbital telescopes are affected far less by our atmosphere, and thus can achieve accuracy to about 1,000 parsecs away. This is still not enough for most stars in our own galaxy, however, as they are generally over 1,000 parsecs away, and the Milky Way itself is about 30,000 parsecs across. Thank you for watching. I hope you enjoyed our video and learned something new today. Until next time, adios!